Okay, we finally did it. We made it out of chapter 7. We're here. We're in chapter 8. Time to talk about gases. And to introduce gases, suction cups. You may be familiar with the concept of suction cups. You put them on glass or some other really flat, smooth surface, and it just sticks there. And you can sometimes hang a lot of weight on it. And they're kind of magical, they're kind of mysterious, because if you feel them, if you put them on your hand, they're not sticky, but they'll just stay on the glass or on the window or on the whatever material it is. How does that work? Well, it turns out that it's pressure. So suction cups, here's our suction cup here in this picture. These suction cups are held on by pressure. So the gas that we are in, we're in a bunch of gas right now, is made up of lots of little tiny particles. And those particles are traveling around constantly, crashing into each other, crashing into the walls, crashing into us. And because there's so many of them, even though they're so small, all of those collisions, when they crash into us, when they crash into the walls, those add up. All of those tiny little collisions add up. And so what happens with a suction cup is you basically push out most of the gas from behind the suction cup, so between the suction cup and the wall. And then there's nothing running into the suction cup from the wall side. The wall is not moving around, crashing into the suction cup, but there's lots of gas particles that are constantly crashing into it, and that force pushes it onto the wall, and that's how it stays stuck. So if you have a 2-inch diameter suction cup, that can hold up 46 pounds of force. You can hang a 45-pound weight on a 2-inch diameter suction cup, which seems crazy. That's just the power of pressure. To get suction cups to pull up, part of the reason that they don't work on surfaces that aren't flat is because if there's little cracks, the air will wiggle its way, worm its way through, and then it starts pushing on the back. And when the force from the back and the front are equal, then it just falls off the wall by itself. So usually suction cups have that little pull tab that lets you pull them up very easily instead of having to fight the power of pressure. So pressure is this force that's caused by collisions of gas particles over an area. Force over an area. And one of the ways that we can explain gases is with the kinetic molecular theory. So kinetic, like moving, molecular, like molecules, and then theory, just a way that we explain or understand behavior, in this case of gases. And the great thing about this model is that it predicts correct behavior for most gases under many conditions. And importantly, it's relatively simple. We don't need a ton of fancy supercomputers to explain our kinetic molecular theory. We can learn it in our Intro to Chem class. So it's not perfect, and it will break down under certain circumstances or certain conditions. We're going to look at places where it works well, which is like conditions that we would be able to exist in as well. So here's our 4 points, 5 points. It used to be 4 points, but now it's 5 points. Just I'm using a different book. So kinetic molecular theory. Our gas consists of tiny particles of matter in constant motion. So you've got all these little particles, be they atoms or molecules or other things, and they're flying around. That's what the little trails are, right? So they're flying around, they're in constant motion. These gas particles, when they collide, they're elastic collisions. Elastic just means that no energy is lost. So if two of these gas particles collide, the energy that they put into that collision also comes out of the collision. They just travel their own separate ways. If you think of like playing pool or billiards or some other balls on a felt tabletop surface, that's the sort of collisions that we're talking about. They're not like hitting each other and sticking and stopping. The energy is being transferred nicely and neatly. The gas particles are also separated by large distances relative to their size. So the particles are really small. The distance between the particles is actually also really small, but because the gas particles are so small, the distance between them is relatively large. So they're not like crammed in like a liquid, but there's empty space between our particles. So we've got empty space between particles. The gas particles also don't attract or repel each other. So when they're traveling towards each other, they're just traveling towards each other. There's not like some sort of magnet action drawing them together or forcing them to soften their blow as they're coming in close to each other. They're also not like covered in atomic Velcro that causes them to stick together. They just collide and bounce apart. They're not sticky or anything like that. And then the speed, how fast the particles are moving, the speed of the particles depends, at least in part, on the temperature. So higher temperature means higher speed. Hot particles move faster than cold particles. So if you heat the particles up, they move around really fast. If you cool the particles down, they don't move around quite as fast. Do we have questions about any of these beautiful 5 points of kinetic molecular theory that you should know? Cool. Okay, so some of the properties of gases that we've, I think, talked about or we have experience with are consistent with the properties of gases and kinetic molecular theory. Those two things are consistent. So we know that gases are compressible. You can squeeze a basketball and it gets smaller. You can squeeze an empty water bottle and it gets smaller, assuming it's not a hard-walled water bottle. So if we take a container with a piston that can move or a lid that can move and you push that lid down, what happens is we're reducing the amount of space that's between the particles. There's empty space between the particles. And so we can push them closer together and get rid of some of that empty space. If there was no empty space, we would not be able to compress it any further. For example, like a table. You can't just like lightly squeeze on a table and boom, it magically gets smaller. Solid objects and liquids don't compress. So because of this empty space between the particles, we can compress them. Gases will also assume the shape of their container. Since the molecules in the gas don't interact with each other, they just crash into each other, they just collide, they don't stick together and lump together. Then the particles are just going to fly in constant straight lines around the container, bouncing off the walls, and they'll generally just kind of spread out. If there's a bunch of particles all at once down in this bottom left corner, for example, when they run into each other, they're going to end up pushing each other out apart, and they'll generally disperse amongst the area that they're in. Like smells of your fast food of choice. In a room, house, or car, or other odors that might come up during a long road trip in a car. They generally tend to work their way around. So that's an example you might be familiar with. Gases also have low density in comparison with solids and liquids, and this is because of the empty space that's between the particles in a gas. So a typical can of soda, just a normal 12-ounce can of whatever soda you prefer, maybe Mountain Dew, if you turn that into a gas, its volume would expand to be the size of almost 2 bathtubs. So you could fill 2 bathtubs with the gas of 1 can of Mountain Dew or cola or whatever you prefer to drink. That's how much empty space there is. versus you could just set it in the bathtub, and there's obviously going to be a lot of extra room. I can picture it in your mind's eye. Can of soda in your bathtub, if you have one. Lots of empty room, tons of empty room, and then double it. So those are some examples, some ways that kinetic molecular theory shows that it's consistent with our experiences. Pressure, which we talked about briefly before with the suction cups, is also a prediction of kinetic molecular theory. It's something that we can create the idea of out of kinetic molecular theory. So pressure is the result of constant collisions between the particles in a gas and the surfaces around them. And pressure does a lot of cool stuff for us. Because of pressure, we can drink from straws, we can inflate basketballs and play basketball, we can play soccer, and we can move air into and out of our lungs. Without pressure, we can't do any of that stuff. Variation in pressure also creates wind. It's not trees sneezing, like Calvin and Hobbes would lead you to believe. And changes in pressure also help predict weather. So one of the ways that weathermen predict the weather with relatively good accuracy, even though it might not feel like that a lot of the time, is with pressure. You can also get like little home pressure and temperature stations, and they can sort of predict pressure. This is also how Grandpa on the porch with his achy knee lets you know that there's a storm coming. The pressure change affects the knee, and then, ooh, a storm's coming, you know, something like that. So the pressure exerted by a gas sample is defined as a force per unit area. So if you take a little cross section of the board, if you draw a little square and you add up all the collisions on that little square in a certain amount of time, average out that force, that's going to give you your pressure. It depends on a bunch of factors, including the number of gas particles in a given volume. So if we look at these two containers, our top container, we've got fewer gas particles than we have in the bottom container. More gas particles in the bottom container, more particles means more collisions means higher pressure. So oftentimes we'll be thinking about, if we're thinking about pressure, how does this affect the number of collisions? How does this affect the force of the collisions? And then how does that relate to pressure? So more particles means, not memes, means more collisions, which means more pressure. Or higher pressure. So if you put in even more particles, how would the pressure change? Would it go up? Would it go down? Up. It would go up. Cool, we're locked in. You can also experience pressure imbalance. For example, you might be aware that atmospheric pressure is lower at higher elevations. So, for example, if you go up to the mountains, you're going to have lower pressure around you. And that change in pressure, going up to the mountains, coming down from the mountains, flying in an airplane, if you've flown in an airplane, there's pressure changes that happen. And your ears are sensitive to pressure because you've got gas inside of your eardrums, and then there's obviously the gas outside the eardrums that we're all in. And that difference in pressure, if it's higher pressure inside your ear or outside your ear, that can cause pain as your eardrum sort of getting pressed in or pressed out. And so if you yawn or if you chew bubble gum or if you have this superpower where you can flex the little muscle in your ear, then that can release the pressure, and then there's no more pressure imbalance. Your eardrum isn't bulging in or out. So if you fly on a plane, or if you go up to the mountains and there's a small baby, an infant, a small child around, they are almost definitely going to cry because they feel pain in their ears from that pressure imbalance, and they don't know how to express, my ears hurt, give me a piece of gum to chew, And even if they did say that, you'd say, no, you can't have a piece of gum to chew, you baby. Babies can't chew gum. It's unsafe. And so that's why babies cry on airplanes. Thanks for coming to my TED Talk. Huh? Yeah, it's like, it's almost an inevitability. If you see a baby on a plane, it's like, that baby will be crying at least twice. Once when we go up, and then probably also when we come down. Okay, so that's cheese. Pressure units. The simplest unit of pressure, in my opinion, is the atmosphere. The atmosphere is the average pressure at sea level. And the atmosphere is so convenient. At sea level, the pressure in atmospheres is 1. 1 atmosphere at sea level. So if you're around sea level, you would expect the atmospheric pressure to be about 1. We're at maybe 400 feet above sea level. So guess what? The atmospheric pressure here is normally also about 1. It's not exactly 1. If we had to guess, is it higher than 1 or is it lower than 1? The pressure here, we're a little higher than sea level. At sea level, the pressure is 1 atmosphere. Is the pressure here normally a little less than 1 atmosphere or a little more than 1 atmosphere? How does pressure change with elevation? When you increase in elevation, pressure decreases. So we're a little below 1 atmosphere. A little less than 1 atmosphere of pressure. So we'll often be using the atmosphere because it's really convenient. The SI unit of pressure, though, so the International System of Units unit of pressure, the metric unit of pressure, if you will, is the Pascal, which we won't use very much. And the Pascal is defined as 1 Newton, not Fig Newton, per square meter. A Newton, I'm not sure exactly what the force size is, but it's really small. And a square meter, right, basically 3.3 by 3.3 feet. It's like 10 square feet. That's a really large area. So a small amount of force over a really large area, it's a way smaller unit than an atmosphere. So 1 atmosphere is 101,325 pascals. So pascals are really, really small units of pressure. And I basically don't use pascals in my class, just because of the way that it is. But it is a unit of pressure. Oftentimes you'll also see kPa. If you're working with something that gives you pressure units on it, it's probably going to default giving you those pressure units in kPa, kilopascals. So it'd be 101 kilopascals with some change. Other pressure units that we have are the millimeter of mercury, and this originates from how pressure was measured with a barometer. A barometer is a device that measures pressure. So a barometer is a tool that we can use to measure pressure. Your phone probably has a barometer built in. If you have a smartwatch, it probably has one built in. You could look at your weather app if you've got a weather app, and it'll tell you what the pressure at the nearest weather station is. The way that barometers originally worked is they would take a really long glass tube. That's what we've got here in the middle. They take this really long glass tube and they would submerge it in a bath of mercury, a big tube, something of mercury. They'd fill it all the way up with mercury so there's no bubbles in it, and then they pull it out of the tube. So they pull this thing out, and at some point there's enough mercury stacked up here that it just doesn't go any higher. So the force, this is the way that straws work also. There's a force that's being exerted by atmosphere on the mercury that's in the bath. And since mercury is a liquid, there's force pushing down on the mercury, and that's going to push it up into this straw. And we've got a vacuum up here because we originally had this sealed off. And so the mercury will only rise as high as there's pressure to push it up into that glass tube. And it turns out that at sea level, that's about 760 millimeters, or 29.92 inches. So about 2.5 feet tall column of mercury. So you have to have a lot of mercury to be able to do this. It's also really bad when they break because mercury is, bad for you. But one of the cool things, and why I like talking about this, is that the unit millimeters of mercury, we're talking about the length of this column of mercury. And so you can actually do length conversions from millimeters to mercury, or millimeters to inches, or inches to millimeters, if you're using those units, millimeters mercury or inches mercury. So I'll show you how to do that later. I think it's cool, but it's a little bit unnecessary. It's a little extra. Any ideas why we don't do this with water? Because water would obviously be a lot safer than mercury. What do you think is more dense, mercury or water? Mercury. It's like 13 times more dense. So if we tried to do this with water, it would be like 30 feet tall, which is a little impractical for like putting on the wall in your classroom. So we can't do that. And then the way that straws work is instead of having a vacuum up here, you've got your mouth, and you just suck a little bit, and that creates a pressure imbalance. And then the pressure outside is greater than the pressure in your mouth. And so it pushes the liquid up. So you're not really sucking the liquid up, it's kind of getting pushed into your mouth, which is interesting. All right, here's some units. So we talked about Pascal, talked about the atmosphere, talked about the millimeter of mercury. There's also inches of mercury, which was briefly mentioned. And we also have torr. And the one that we are probably familiar with, if we're familiar with one of these, pounds per square inch. Pounds, unit of force, per square inch, unit of area. Arguably the most straightforward unit of pressure because it's actually force per unit area. And then we've got average air pressure at sea level over here on the right. So 1 atmosphere is equal to 760 torr, is equal to 760 millimeters mercury, is equal to 14.7 psi, and so on and so forth. So we can take any of those two numbers, any of these two numbers that we want, pull them out, and make unit conversions. And for whatever reason, torr is the same as millimeters mercury. You can just swap millimeters mercury and torr out for the other, and the numbers will be the same. Questions so far? All right, we're having a good time. So let's say that we want to convert 1.25 atmospheres to torr. So we're starting with atmospheres. We're going to torr. We're going to find the two things we care about over here in this table. So we find 760 torr. We find 1 atmosphere. We're going to pull those things out. So 760 torr equals 1 atmosphere. And that's what we would use to make our conversion factor. So starting with our 1.25 ATM, we use 760 torr on top and the 1 atmosphere on the bottom. This gets our atmospheres to cancel. And then we ask our calculator to please tell us what the answer is. it is 950 dot torr. We maintain our 3 significant figures from our first number. So if you haven't been doing unit conversions in a while, this is like a sort of a brief recap of how we can do that. If we're starting with inches mercury and we want to go to millimeters mercury, we're going to pull out the 2 things that we care about. Let's do that in purple. So millimeters mercury, inches mercury, Hg is mercury. So 760 mmHg equals 29.92 INHG. You'll sometimes, occasionally maybe, hear me pronounce those as words, and that's just me being silly. So 30.15 INHG. Our conversion factor, we want the INHG part on the bottom, and the 760 mmHg on top. This makes our inches mercury cancel out, because we had 1 on the top, 1 on the bottom, so those cancel. And once again, we turn to our calculator and say, please let me know what the answer is. And it is 765.8 mmHg. We can also do this, since it's between inches mercury and millimeters mercury, we can do an inches to millimeters conversion. I don't really expect you to know how to do this. It's just kind of fun, which is why I'm showing you. I think it's fun, so you probably don't. 2.54 centimeters equals 1 inch, so 25.4 millimeters. Oh, I'm doing a great job at writing today. 25.4 millimeters equals 1 inch. So if we multiply by 25.4 millimeters, divide by 1 inch, the inches part cancels out, and 30.15 times 25.4 gives us, look at that, 765.8 millimeters of mercury. So it also works as a length conversion, which again is more just, I think it's fun and cool, than it is necessarily useful. Questions about those? Okay, one for you to do. Convert a pressure of 4,394 millimeters mercury into pounds per square inch PSI. Okay, what are the 2 units that we have in this problem? What are the 2 units? PSI? What's the other one? mmHg. So in our table up here, I left it sort of on the screen on purpose. So mmHg, right, at sea level, it's 760 mmHg. Pounds per square inch, it's 14.7. So those are the 2 numbers that we're going to use to do this conversion. We're going from mmHg into pounds per square inch, PSI, and 760 mmHg equals 14.7 PSI. Since we have millimeters mercury, the conversion factor that we make from this is going to be the one that has hopefully the one that has 760 millimeters mercury on the bottom. So we divide both sides by that. The left side magically turns into 1, and our conversion factor is 14.7 psi over 760 mmHg, millimeters mercury. Then we take our given 4394 mmHg. We multiply it by 14.7 psi. We divide by 760 mmHg. Units cancel. And we're left with 85.0 psi. I'm pretty sure the psi number is not exact, so that's going to limit our significant figures. So it's more pressure than we'd probably put into our mountain bike tires, but if we have a road bike, it's kind of in the ballpark. It's a little low, maybe. Definitely high for a car tire. If your car tires are at 85 psi, get checked. You and the tires. Okay, so that's pressure units. Now on to the fun stuff, the formulas. So we've got a bunch of simple gas laws. We're going to talk about, I think, 4 of the simple gas laws. There's not just 4, there's more than 4, but there's 4 that we'll focus on. And you've got a couple options when it comes to simple gas laws. Boyle's law, which we're looking at here, is one of our simple gas laws. One of your options is you could memorize all the simple gas laws. The other option is there's a way that we can use algebra and a gas law that we'll learn later on to make all of the simple gas laws. You can just make them upon command as long as you can command algebra. So if you're scared about memorizing a lot of stuff, there's another way. Now let's talk about Boyle's law. So Boyle's law relates pressure and volume. So the pressure of a gas, the amount of force that the gas applies on the walls of the container, depends in part on its volume. So you can change pressure and that'll change volume. You can change volume and that'll change pressure. The two things are related. As long as the temperature and the amount of gas are constant, the pressure increases for a decrease in volume. So if volume decreases, then pressure increases. So if you shrink something, like if you take an empty $1 water bottle, the plastic kind, and you squeeze it, you twist the heck out of it to make it smaller, that increases the pressure inside, and so then you flick the top of the cap and it goes flying into the air or into your friend's butt or wherever you decide to shoot it. Right? This is a practical application of Boyle's law. Squeezing a basketball would be another example, or any other inflatable ball. It doesn't have to be a basketball. If you squeeze it, right, it gives a little bit. It gets harder to squeeze the more that you squeeze it in, because you're decreasing the volume more, and that's increasing the pressure more, and so then you have to push harder to get the volume to go down more. This is also how you inflate tires. If you've got like a hand pump, so this is a tire pump. So we've got the tube part of the tire pump, that's where the action happens, and then you've got the handle that makes you feel like you're an old-time prospector trying to blow up some TNT that just won't go for some reason. So when you pull up on the handle, there's a one-way valve on this, the shaft of the tire pump. There's a one-way valve that lets air in. So now the pump is full of air, and then when you push down, that one-way valve doesn't let the air out, and so you're instead forcing the air through the tube or through the hose and then into the tire, whatever you're trying to fill up. And if you've ever inflated a basketball or a tire, or God forbid, a car tire, then you probably know the further that you go, the closer you get to your goal, the harder it is to push down, or the farther you have to push down before it finally makes that and air goes into the tire, right? That's because of Boyle's law, essentially. So the closer that you get, the further you have to push down, the more you have to decrease this volume to get the pressure to increase high enough that it'll actually go into the tire. So on the upstroke, you're allowing air in, and the pressure in here is just the pressure of the air around us. And then as you push down, it compresses down to a smaller volume, and the pressure is greatly increased. And you just do that ad nauseum, sometimes literally. So the relationships between some of our gas properties, like pressure and volume, are described by gas laws, and these are named after old dead men. So the first one is named after Robert Boyle, who's been gone for a while now. Boyle's law assumes constant temperature and a constant number of gas particles, which will always be the case when we're using Boyle's law. So Boyle's law states the volume of a gas and its pressure are inversely proportional, and the way that we express that mathematically is V alpha, or fish sign, 1 over P. So this sign means is proportional to. That's what that means. And then 1 over P is the inverse of pressure, so that's where the inversely part comes from in the proportional part. For those of you that like math, the one of you that's in the room, you may know that you can also substitute in an equals and some constant and make it equals K 1 over P, where K is just some number. We don't know what the number is, but it's some number. It's a constant. It doesn't change because it's a constant. And so from this, if we multiply both sides by P, P disappears from the right side. It appears on the left side. It moves to the other side. And so we get PV equals K. And what is K? A constant. So does it change? No. So if we change P, then V would have to change. If P goes up, then V would have to go down so that it's still equal to K. And the projector shut off. Okay, we're back. So PV equals K. Now if P changes, or if V changes, then that would also be PV, but it would be a different PV. So we can separate our first set of P and V and our second set of P and V, and we get P1 V1 equals P2 V2. And that's the part that you'd probably memorize. So I'm going to show you this just on this slide because most of you probably don't care about the math. It's not really that important for the class, but sometimes it helps to know how we got somewhere. So that's how we got there. For the 0 of you that were wondering how we got from one thing to the other. So P1 V1 equals P2 V2 would be the one that you'd memorize for Boyle's law. So looking at how Boyle came about with this information, if you take this little tube that has air in it, believe it or not, there's air in there. That's the green part here. It doesn't show up well because it's also gray, and the mercury is silver, and gray and silver, as it turns out, are very similar. Okay, so now it's green, so you can see it. So on this far left case, we've got some amount of gas, air, that's trapped in our little upside down candy cane. And there's a certain amount of mercury in there. If you add in more mercury, that's going to increase the pressure. We're increasing the amount of mercury that's pushing on this gas. So we increase some of that, and the volume decreases. We increase it to 3 times the original amount, and the volume has decreased to 1/3 of that. And so what Boyle did is he plotted this data, and it would have looked something like this. So we've got a plot of volume, pressure, So as we're moving left to right, our volume increases. As we're moving down to up, our pressure is increasing. So at really high pressure, we've got really low volume. At really high volume, we've got really low pressure. And there's this shape. And the mathematically inclined amongst you may notice that that looks like a 1 over x function. And it turns out that if you plot instead 1 over pressure, so this time we've got still volume on the x-axis, we've got pressure on the y-axis, but on the right side we've got 1 over pressure. If we plot it as 1 over p and v, now it's a straight line. And straight lines are really convenient. They're a lot easier to describe mathematically. So this shows us that we've got a linear relationship between the inverse of pressure and volume. So when volume goes up, the inverse of pressure also goes up. It's just more math showing us why P1 V1 equals P2 V2 works. Kinetic molecular theory also explains Boyle's law. So if we have a container that has the same number of particles inside, we move one of the walls of the container down, we drop this plunger down. Now we've trapped our gas particles. They're in a smaller space. Since they're closer together, it's going to take them less time before they run into something, either other particles or the walls of the container. So we get more collisions. And what does more collisions mean? Higher insurance rates. But in the context of the slide, more collisions means more pressure. Right, so kinetic molecular theory also explains this. Questions so far? Okay, now the magical moment that you've probably all been waiting for. How do we use it? How are you going to test us on this on an exam? Here's how. So a sample of gas has an initial pressure of 2.44 atmospheres. Initial pressure, 2.44 atmospheres. And an initial volume of 4.01 liters. Initial volume, 4.01 liters. Its pressure changes to 1.93 atmospheres. What is being our question words, the new volume? So what is the new volume? With these problems, these gas law problems, we're going to have a bunch of variables. It's helpful if we write those variables out on the side. So we've got a pressure that's given to us, 2.44 atmospheres. It even tells us that it's a pressure. That's nice. We've also got a volume that's given to us, 4.01 liters. And we've got another pressure. It's 1.93 atmospheres. And because we memorized our Boyle's law, we know that P1 V1 equals P2 V2. The part here at the end, this if temperature and amount are kept constant, is just so that somebody wearing a fedora can't just say, actually, you didn't specify that they're constant. That's the only reason that it's there. It just lets us know that we can, in fact, use Boyle's law. There's not some sneaky trick that we've got up our sleeve. Okay, so the important part with all of these gas laws, all the simple gas laws, is that we get our pressure and our volumes paired up correctly. We've got two pressures. We've got one volume. Which pressure does our volume pair with? Does our volume pair up with the 2.4 atmospheres or the 1.9 atmospheres? Which one is it? Be bold. All right, well, somebody said it, I think. 2.44 atmospheres. The correct answer is that these first two go together. We know that that's the case because they said initial pressure and initial volume. So those both were given the tags in the text that said initial. Those both go together. And we're having fun with our projector today. So I'm going to label these both 1. It doesn't matter if you label them 1 or 2 or Bob or 15. You can label them whatever you want, just as long as they stay together. And then this other pressure, we're going to label 2 because it's not going along with the first ones. And then the thing that we're looking for is the one that we don't have, which is V2. So we need to rearrange P1 V1 equals P2 V2, our Boyle's law, so that V2 is by itself. So we have to do a little bit of algebra. We divide both sides by P2 to get it to cancel out on the right side. And then I'm going to flip it left and right so that it's convenient. So V2 equals P1 V1 over P2. And we can plug in P1 times V1 on the top. So we put in our numbers now. And then on the bottom is our P2, our 1.93 atmospheres. Our atmospheres cancel, and we're left with units of liters. And we round this for 3 significant figures, so it's 5.07 liters. Questions? Okay. We also have Charles' law. Charles' law relates volume and temperature. So instead of P and V, it's V and T. You may know that hot air rises. So all this stuff I've been spewing all class, right? It's all going to the top of the room if it's not been trapped by my mask. So if you heat a gas, that increases the volume. So you're increasing the space that it takes up. But the mass of that gas doesn't change. So you've spread out the volume, but the mass is the same. And so the density decreases. The volume increases, so the density decreases. So hot air is less dense. And what do things that are less dense do? What do witches do? What do ducks do if you throw them in a lake? They float. Monty Python reference. So a lower density gas floats in a higher density gas, just like wood floats in water. And so the reason that hot air balloons can stay up is because they're full of low density gas. Full of low density gas relative to the air that's around them. And so that causes them to float up into the air if you've got a large enough balloon. This also happens at much smaller scales. So if you live in a 2-story building, the second floor tends to be warmer than the first floor because hot air rises because it's less dense. Cold air also sinks because it's more dense. So volume increases with temperature. And if you plot some data of temperature and volume, if you extrapolate, so if you go beyond the scope of your data, if you extend this line out past your data, then this line should collide at a zero volume at negative 273 Celsius. Because negative volume is impossible. You can't have negative volume. Space doesn't fold in on itself, at least in that way. And so this negative 273-ish Celsius we call absolute zero. You can't get colder than that. That's as cold as it gets. And coincidentally, that's 0 Kelvin. So the Kelvin scale is based on this law, which is not here. Yes, it is. I just didn't read far enough. So J.A.C. Charles, no doubt the J.A.C. stands for something absurdly French, was a French mathematician and physicist and quantified this relationship. So Charles' law assumes constant pressure and a constant amount of gas. So Charles' law takes the volume of gas in its Kelvin temperature. Just do something real quick here. Don't mind me. And its Kelvin temperature are directly proportional. So volume, Kelvin temperature, directly proportional. When one goes up, the other goes up. When one goes down, the other goes down. Now, what do we think might be important about using Charles' law? Is there perhaps a unit that needs to be in a specific set of units, type of units, for us to use Charles' law? Any guesses? Anyone else? Yes, it needs to be in Kelvin. That actually worked out really nicely. It needs to be in Kelvin temperature. The units of temperature have to be in Kelvin. What units do the temperature have to be in? Kelvin, that's right. Okay, so when the temperature of a gas sample, I'd like to point out that it's in kelvins, is doubled, the volume doubles. And again, just to drive it home, the temperature needs to be expressed in Kelvin. So the equation of the line, this line, right, we can describe a line with y equals mx plus b. So we can use y equals mx plus b, where b is our y-intercept. And if we use the Kelvin temperature, the y-intercept, this b term, is 0. Which temperature scale are we using? The Kelvin temperature scale, that's right. So again, when we're using Kelvin, the y-intercept is 0, and that makes everything nice and simple. Just y equals mx, where y and x are volume and temperature, respectively or not, it doesn't matter. Okay, so kinetic molecular theory also works with this. If the temperature of a gas sample is increased, the gas particles move faster. Hot gas moves faster than cold gas. For the pressure to remain constant, the volume must increase. So since they're moving faster, they have more energy. They also have more energy. If you get in a car crash at 5 miles per hour, how does that compare to getting in a car crash at 50 miles per hour? Which one's worse? 50 miles per hour. Why is 50 miles per hour worse than 5 miles per hour? There's way more energy, right? 50 miles per hour, way more energy. 5 miles per hour, you're probably just driving away and you just exchange, information. There's way more energy when you're moving faster, and so those gas particles, even though they're really small, also move faster. They collide with more energy. That increases the force, that increases the pressure. And so the volume has to increase for the pressure to stay constant. You can do Charles' law at home if you have a balloon. So what you're going to want to do is you're going to want to put on a cowboy hat. I know that many of you have cowboy hats. You're going to want to put on your cowboy hat. You're going to blow up a balloon. Don't blow it up all the way because it'll probably explode. So you're going to blow it up part of the way, halfway maybe. And then you can put it in some ice water or run it under cold water, put it in your freezer, and then come back later and you'll notice, oh, my balloon got smaller. You pull your balloon out of the freezer or out of the cold water and you run it under some warm water, and you'll notice that it starts to get bigger. You haven't opened up your balloon at any point and added in more gas. That's just the pressure of the gas increasing, and since it's a balloon, the volume can increase or decrease. So that's all that's happening. It probably won't be super extreme, but it's something you can do at home. All right, we've got a balloon. Yay. The balloon, I forgot to circle this. Okay, look at this. That's what you'd memorize. V1 over T1 equals V2 over T2. Okay. V1 over T1 equals V2 over T2. A balloon is filled to a volume of 2.20 liters at a temperature of 22 degrees Celsius. The balloon is then heated to a temperature of 71 degrees Celsius. Find the new volume. So we've got volume. I'm going to put volume in the middle. It's 2.20 liters. We're given a temperature, 22 degrees Celsius. We're given a different temperature, 71 degrees Celsius. Now we have to ask ourselves, which temperature does our volume go with? Does our volume go with 22 degrees Celsius or 71 degrees Celsius? This is arguably the most important question, the most important part of this whole question. It's not, but you could argue that it is. Which one does it go with? It goes with the 22 degrees Celsius. So we're going to call these, because I think most people will probably call them 1. You could also call them 2. It doesn't make a difference. So we're going to call those 1. We're going to call our other temperature 2. The reason that we know these two go together, volume of 2.2 liters at a temperature of 22 degrees Celsius. So this at a temperature, this links these two things together, then heated to a temperature of 71 degrees Celsius. So that separates our 71 degrees Celsius. And we want to find the new volume, which would be V2. So we're finding V2. To find V2, we multiply both sides by T2. We get V2, and we're going to combine the T2 on the top. So T2 V1 over T1. You could write V1 T2. It doesn't matter. You can flip them around because multiplication works that way. Are we ready to plug in our numbers? What units do we need our temperature to be in? Kelvin. Our temperature needs to be in Kelvin. That's why I underlined it so many times. So we have to convert to Kelvin. We do that by adding 273.15 Kelvin to both of our temperatures. And I'm just always running out of room. So we'll make some more room. 22 plus 273.15 is 295.15 Kelvin. And our other one, 344.15 Kelvin. The underlines are there so we know where our last significant figure is. Questions? Cool. Can we plug our numbers in now? Yes. Okay, so we plug in T2, 344.15 Kelvin. We plug in 2.20 liters. And then on the bottom, T1, 295.15 Kelvin. And our kelvins cancel. The units that are left are liters. So 344.15 times 2.2 divided by our other temperature. our new volume, 2.57 liters. Does that answer make sense? Is it reasonable? What changed? What was our variable that we changed in the problem? Temperature went up. When things get hot, they expand. So like, you've probably experienced this with like a water bottle. If you've used a water bottle that seals, if it's full of cold water, you leave it in the car, and then you go to open it up, whoosh, as the hot air is now releasing. The pressure inside is increased and it's releasing. So we expect it to get bigger. 2.57 liters is a larger volume than our first one. Okay, here's one for you to try. V1 over T1 equals V2 over T2. Give this one a shot. All right, we've got volume of 45.8 milliliters, ml, and we've got temperatures, 25 Celsius. We've also got 100 degrees Celsius. Which of these two temperatures does our volume pair with? It pairs with 25 degrees Celsius. So we are told that this is an initial volume of 45.8 milliliters, and it's heated from 25 degrees Celsius, the from indicating that that's our initial. So those are our state 1s, and then we have our state 2, and we are again looking for V2. So we rearrange. V2 equals T2 V1 over T1. If we plug in our numbers now, we will get the wrong answer. What do we need to do first? We'll dance. And then we convert to kelvins. So add 273.15. And then we can plug our numbers in. So we have to always be working in kelvins. So 373.15 Kelvin times 45.8 milliliters divided by 298.15 Kelvin. Kelvins cancel. We get 57.3 milliliters. We were asked for the volume in milliliters, so we don't have to do anything. These are the correct units. Any questions?